All right. So now we're going to talk about something called electric flux. And this ends up being a very powerful approach as a way of quantifying electric fields. So we've spent a lot of time now thinking about how charges, positives and negative charges, create an electric field. Those are not the same thing. And this electric field, which is created by this charge, is a way of letting that charge know its existence around the world, around the universe, really. And so, particularly if there are other charges nearby, then the presence of the electric field tells the other charges what to do, whether they should be repelled or attracted. And we've talked about how we can quantify this as a vector field, where we can draw little arrows everywhere, specifying the direction. Maybe the length of the arrows correspond to a magnitude, as well as electric field lines, where we can have lines that what Faraday called lines of force that go out from positive charges and go into negative charges, just like the electric field. And their density, the density of field lines corresponds to the magnitude, and the direction corresponds to the direction that a force would feel for a positive test charge, or the direction a positive test charge, the force that a positive test charge would feel, rather. We are now going to then think about this idea of flux, which is in a sense a way of kind of counting field lines that are passing through surfaces. And this turns out to be very, very powerful because it's going to introduce this idea called Gauss's law that we will do next time, which is one of the four kind of big ideas in this course. So this results in what's called Gauss's law, which we will do next time. Now, this idea of flux, I think, is better introduced thinking about kind of how water flows. And we can talk about the flux of water through a surface. And then we'll find that I think the more intuitive ideas of water flow, there's going to be a nice analogy that carries us to electric field lines. So we're going to talk about most of this lecture in terms of water flow and this concept of streamlines. And it turns out these ideas of streamlines are going to be completely analogous to electric field lines. But I think it's a little bit more visual thinking about water. So here's the idea to define terms. Imagine you have water flowing down a pipe. So I have two pipes here. One is thinner than the other. Water is flowing in this direction with some velocity, v. If you placed a sensor at the end of the pipe, which I designate by this kind of red waffle thing, and that sensor measures the mass flux, then that sensor is asking how much mass flows by in a given amount of time. So if this is some sensor that's keeping track of how much mass is passing by that sensor in a given amount of time, it can then return back a rate. A rate being, the amount of mass that was flowed by in a certain amount of time. So the idea is that we want to try to measure, with this hypothetical sensor, how does it quantify what delta m, or what amount of mass, flows by the sensor in a given amount of time. And that amount of time could be variable. It could be passes by in 1 second, could be passes by in a minute or an hour. So we're going to let the delta t be variable, which is why I'm rating this as a delta m. How much mass, the amount of mass that passes by the sensor, I'm going to write as delta m, not because it's a change in mass, but again, thinking about what we've been doing the last couple times, it's going to depend on this delta t. Or if delta t is a second compared to if delta t is an hour, that's going to be a much different amount of water that's going to flow by the sensor, if delta t is a second compared to an hour. So the amount of mass is going to be some function of delta t. And, as you might imagine where we're going, if I want to make delta t smaller and smaller and smaller, then this delta m gets smaller and smaller and smaller. And I'm going to eventually be able to write things in terms of, say, instead of delta t, I'll write dt. And then this becomes dm. And then the mass flux, in this case, is dm by dt. It's just the derivative of mass with respect to time, or the rate that mass flows by in a given amount of time. So the first question we could ask, if we were to come up with a model, what variables play a role in determining how much water flows past the sensor? And we've already answered one of them, which is going to be the length of time, delta t. I imagine as if it's measuring per minute versus per second, that's a different amount of mass that's going to flow by. What else do you imagine impacts how much water flows by this given sensor? Well, it's probably going to have to depend in some way on the speed of the water. All other things being equal, if the water is flowing down the pipe faster, then more water is going to flow by the sensor. I keep referring to water, and if I want to translate that into a mass, right, when I think of these pipes, really what I'm thinking about is how much volume is passing by a sensor. So if I want to then translate that to mass, I'm going to need to know something about the density. So the density of water, which I'll write as rho sub w. And then I've done these two drawings to imagine, again, all other things being equal, they're both water, the sensors are measuring for the same amount of time, they both have the same speed, v, for both of them, that this bigger pipe, more water is going to be passing by. I don't know why my pen has stopped working. More water is going to pass by in a given second, say, compared to the small pipe, just because there's more water to pass through. And what's determining that value? In this case, it's kind of the width of the pipe. But we can think about that's really what's going on. It's the kind of this area that matters. It's this area being bigger than this area that is going to differentiate how much water flows past the sensor. So we could also say something about the size of the pipe, which in this case we're going to quantify by the cross-sectional area. All right, again, you cut the pipe, and the kind of the cross-sectional area is just going to be the area of the pipe, kind of what I've drawn as the sensor, or drawn these two areas on the left. And so, now if we can think, how do we put these all together in order to get a mass flux, a dm. I also ultimately want to calculate how much mass dm flows by in a given amount of time. How does that depend on these four variables that I've just listed here? Well, you could proceed by dimensional analysis. It turns out there's only one way you can really combine all the four of these things and get units of mass. But again, if we're thinking about, that it's some fluid flowing past the sensor, right? Really what we're thinking about is that there's some amount of volume that flows past the sensor in a given amount of time. And then we can turn that into a mass because mass is density times volume. So I can imagine that this is going to be rho water times the volume that kind of flows past in delta t. All right, some section of that pipe, the water in that section will flow by in some delta t. And to see what I mean, you can imagine that if delta t is a microsecond, and it's really only the water that's kind of right here that's going to have enough time to flow past. the water that's over here, it's going to proceed forward a little bit. It's going to come nowhere near close enough to get all the way through. If delta t is a second, then this stuff that got through in a microsecond is definitely going to get through. And then this stuff is going to as well. This stuff is going to as well. There's going to be more of the pipe that can make it through in a second. If delta t is 3 seconds, then all that stuff is going to get through, but then so is this, and so is this, is all going to get through in 3 seconds. And so we can think of if volume is an area times a length, and we already have the area, so now I just need a length. Right? Because if I take this area and then add and then multiply by a length, that's going to be the volume of some cylinder. The cylinder of water that does make it through the sensor. And the amount that's going to be relevant is because it's going to depend on this V. This V determines, in some V delta T, which is the distance, that's some length, V delta T. And if you think about it, it makes sense that that is the length of the pipe, where all the water within that length will make it through the sensor in some delta T. So we could think of, say, nope, that was too big. We could think of, this volume here. That volume is going to be the volume of water that in some delta T, enough time has passed. That in that amount of time, that kind of slice of water of the pipe will make it through the sensor. So, putting this all together, it looks like then this becomes rho water times A times V delta T, or that delta M is rho water V A delta T. And that does then combine all the kind of quantities we talked about, and I think it makes sense, that it depends on them in the way that they do. If the water is flowing faster, more mass will flow through. If the area of the pipe is bigger, more water will flow through. If delta T is longer, more water will flow through. So in this case, you can imagine that if we let delta T get smaller and smaller and smaller, such that we can write it as a dt instead, then a little bit of mass that gets through the sensor is going to be rho water V A times a little bit of time. Or we can talk about then the mass flux past the sensor, dm by dt, is going to be rho water V times A. And so this is, for fluid flow, what we would call the mass flux. And to stick with the variables that your book uses for flux, which uses Greek letter phi, we'll call it phi sub m, rho V times A. And of course, we could always do a sanity check. Do the units actually work out? Rho VA. Well, in that case, rho is a mass per volume, so mass per length cubed. V is a length per time, and A is a length squared. And it looks like the lengths all cancel, and I get something that has units of mass per time, which then matches dm by dt, mass over time. So this all looks pretty well and good for thinking about mass flux through the pipe. And here I've written it so that kind of this rho v here, that is saying something about the property of the fluid, right? What is flowing through the pipe. And this A kind of incorporates property, of the pipe itself, which might be helpful in what we do next. So there's a simple example of what we talk about when we talk about flux. In this case, how much flux of mass flows past the sensor down the pipe. Now let's upgrade a little bit and think about rainfall. So suppose you want to measure rainfall. It's raining outside, you want to measure how much it's raining. You probably did this as a kid, right? One way to measure rainfall is you could go outside and you could place a bucket outside and measure how fast, or when it's done raining, you can measure how much the bucket is filled up, and then that tells you something, given how long it's been raining. So suppose in this situation, just to set the stage here, you want to measure rainfall, and so you go outside and you place several buckets outside. So here you are. So you place one bucket. It's kind of just an open tin can or something like that. You place another tin can out, but don't notice that you kind of put it on a rock, so it's kind of at an angle a little bit. Not knowing what to use, there's wine decanter for, right? You put one of those out, which has a kind of very thin opening on top, with a big base. And then your friend also, not wanting to go outside, watches through a window while it rains. And the rain could be falling at an angle. It could be falling vertical, but if there's wind, the rain will be falling at an angle. What determines the rate that the buckets fill up? Do all of these fill up at the same rate? Or do they fill up at different rates? Does your friend get wet? Under what conditions does your friend get wet if they're standing inside an open window? Is the formula that we wrote down last time essentially what we want to write down this time? Well, we can think about what's different in this case, and maybe we can generalize. First thing to think about is that the rain has to enter the bucket in order to be counted. So the rain has to flow past some quote-unquote sensor for it to count. So it makes sense that the area that we're going to talk about here is going to be the area that's kind of the opening of your buckets. So in this case, some of them are larger, some of them are smaller. And if your friend is going to get wet, rain has to flow past the window. So we have these things, and we can quantify that as the relevant area that water has to flow through in order to either go into a bucket or get your friend wet. It makes sense that a density should be involved as well, but it's not going to be just the density of water, because it's not a waterfall. If you were to say put this bucket under a waterfall, then the density of water would be appropriate, because essentially every part of space is just liquid water. For rain, there's, of course, water droplets. There's lots of water in the air, but there's a lot of air in between the individual water droplets. The overall density of water is much, much lower than 1 gram per cubic centimeter. So it's not going to be the density of water that we want, but it's probably going to be something like the density of rain, which for kind of moderate to heavy rainfall turns out to be about 1 gram per cubic meter, where water is 1 gram per cubic centimeter. So the density of rain, it's about a millionth, that of water. You can estimate that or look it up. Let's just take it as a given. So it makes sense that there should be some area involved, right? The area of kind of that the water has to pass through to fill up the bucket. And if we're going to talk about mass, then we need some way of translating a volume into a mass. So it makes sense that the density of rain might be relevant. And you might think that, of course, the velocity of the rain is going to matter too. If it's really downpouring and it's kind of coming down, quickly, that's going to fill the bucket up a lot faster than if it's kind of, a light mist, where the rain might be actually experiencing a lot of, drag, and it's kind of getting whipped around by the air versus just falling. So you might think maybe it's the same formula, rho, but we'll use rho rain, times A times V. But if you think about it, the answer cannot just be the same formula we wrote down last time. And again, with these things, it's always nice to kind of think of simple counterexamples. What's a counterexample that shows it can't simply be this? Well, I could think that if the rain is falling perfectly vertically, my friend would not get wet, because nothing's going to be passing through the window. Something has to be kind of going at an angle, so that something goes, the stuff that doesn't hit the roof, it goes through the window and hits my friend, which it would not do if it were perfectly vertical. And we haven't really incorporated anything about the direction of the rain. Similarly, if a bucket's tipped over, then obviously no rain's going to enter at all. You might think that's kind of a silly hypothetical, but that's nonetheless, right? We should have a model that could incorporate, if the bucket is tipped over, then we have some area that it has to pass through. But in this case, the rain is not going to pass through that area at all. So in that case, the mass flux into the bucket, I would say 0. So we need to say something clearly about the geometric orientation. That's what's kind of missing here. And this has to be something about the direction of the rain, and the kind of orientation of the bucket. Because I just gave you 2 examples of how the geometry of the rain dictates whether it goes in the window. Then the orientation of the bucket dictates whether it goes into the bucket. There probably has to be some combination of these 2 things. And does it mean that then this bucket is measuring the same amount of rain or a different amount of rain than this bucket? Even if they're identical buckets, one just is kind of sitting on a rock at a slight angle. What's going on? Why does the orientation matter at all, I guess is the first question. Should the orientation matter? Well, we gave this counterexample here. If it's tipped over, obviously then nothing enters the bucket. So we know that orientation should matter. But you might say, okay, well, that's an extreme example. For these 2, why should the orientation matter at all? If it's raining everywhere, then why should it matter if it's slightly tilted versus not tilted at all? They're the same areas. It's raining everywhere. They both should fill up at the same rate. Perhaps that's your hypothesis. Well, again, we could test that. You could measure that directly, actually do an experiment. But I came up with this simple idea that I think works quite well in trying to explain whether or not this matters or not. What if the bucket is rotated by some angle theta that perhaps is not 90 degrees or something crazy? Let's imagine I have a bucket, that's kind of laying completely level, but it's going to have a false bottom on it, such that the rain that falls through that bucket then is going to fall potentially through another bucket that's beneath it. But what I'm going to do is I'm going to rotate that bucket by some angle. I'm going to line them up like so. I'm going to line them up so that the edge here, I did not do a very good job. That's okay. Power of the marker, I can move things around. Move this over. I'm going to move this over a little bit so that we're kind of aligned on one side like that. There we go. That's good. That's good. And so those vertical lines are just kind of giving me the vertical orientation of the buckets, which the second one is rotated by some angle, that angle being theta. And they're identical buckets, right? You saw as I was moving around, all I did was duplicate the top one and rotate it. I didn't make it bigger or smaller. So they're identical in every way, just as rotated. So then when I think about the mass flux that goes through the top bucket, which, let's see, what's the best way to draw this? Let me just draw it as a bunch of vertical lines. I'm going to duplicate them so I can have some rainfall going on. I don't want to make it bigger than the bucket. Okay, those look big. Scooch these together. I want to make them more or less evenly spaced apart. There we go. So if I have rain that is falling through the top bucket as so, then there's some amount of mass flux. We'll say four streamlines. We could think of these as streamlines. That they're showing me the path that the water is flowing. And then if you go down, that mass flux, this one on the left makes into the bucket. This one on the right makes into the bucket. The one on this, just kind of barely makes into the bucket. Then this one misses the bucket entirely. So there is a streamline. I meant to get rid of this here. There is a streamline in this case that the mass flux that went through the top bucket, right, so the kind of mass flux here is greater than the mass flux here. And they're identical buckets. The only thing I did was rotate, which shows that the orientation is going to impact the flux. Less water falls into that bottom bucket simply because it's rotated. And then we can also do, I'm going to duplicate it again, move it over here, and I'm just going to rotate it back to being horizontal. And then notice that what if what I had drawn over here on the right, what if that was a regular horizontal bucket, but the rain was falling at an angle. Where here rain is falling vertically downward. Well, in the case on the right, essentially this is showing that the situation on the left is equivalent to if rain kind of falls at an angle. At an angle here. All right, in this case, on the left, rain fell through this bucket, but not all that rain fell through the second bucket. Simply because it's rotated, the orientation of the bucket decreased the flux. Less water literally flows into the second bucket. Similarly, in this case here, where the rain falls at an angle, these streamlines are the only ones that could have made it into the bucket, but one of them misses because of this sideways velocity component. Less water really does flow into this bucket simply because the water is falling at an angle. So there is this geometric result, right? The orientation of the bucket or the orientation of the rain relative to the bucket seems to be what matters. All right, in this case, we could think of, if I draw a vertical line, then, right, it's kind of this angle here, this angle, or this angle, or this angle. That's theta in this case. The fact that the velocity is kind of flowing in at an angle. It's not vertical, but there's some theta relative to the vertical. Decreases the amount of rain that makes into the bucket. So we need something that can quantify this, which was not in our original formula. It seems like we need to talk about things in terms of vectors, right? If I'm talking about the direction of the rain or the orientation of the bucket, I need a vector. Now, the vector for the velocity makes sense, right? That tells me the orientation of the velocity. But how do I describe the orientation of the bucket? Well, here we have to introduce a new idea. So let's define a vector that does exactly what we want. And maybe a little bit more, and it'll become obvious why we want this to be the case. So we're going to define a vector A. And it's going to be kind of an area vector. It's going to only be a vector that's corresponding to a surface. So I can only really define this vector for a surface. And the surface, physical or not, what do I mean by that? It doesn't have to actually be a physical surface. Like I could define this vector for the top of the bucket, which is actually an opening. Right? There's nothing actually there, but I can still define the surface defined by the opening. And I'm going to call this vector A, And the orientation of A is going to be that A is going to point perpendicular to the surface, such that then the magnitude of A is the area of the surface. So in the cases here, right, if I have some bucket, and there's a well-defined surface that is the top of the bucket, right, the hole at the top. I could define that as a surface, and then perpendicular to that surface, I could draw my vector A. So notice that it's perpendicular. If this is the surface, A points perpendicular to that surface, such that, again, the magnitude of it is then equal to the actual area of that opening. And then again here, notice how this is how the orientation gets involved. Same bucket, I've just simply rotated it, but then the area vector points in a slightly different direction, such that it points kind of to the upper right. Still perpendicular to the surface, but now it's just oriented. So it's giving us an orientation of how this is kind of aligned or oriented. Here's another kind of quick, simple example. Suppose I have this kind of rectangular slab. One length is 5 centimeters, another is 3 centimeters, another is 2 centimeters. I could talk about, and there are 6 sides to this thing. So I could write down 6 different area vectors, one for each surface, one for each side. Let's write down 3 of them. So this top surface, right, that's some surface. I could define some area vector, I'll call it A1, that it looks like A1 as a vector is going to be, well, the area is 5 centimeters times 13 centimeters. Right, that slab is 15 centimeters squared, and seems to be pointing in the kind of z direction. Let me throw some axes down. Right, if this is z, this is y, and then that is x. And again, what is this saying? It is pointing vertically upward. It has a magnitude that is equal to the area of this thing, and it is perpendicular to this slab. Right? If you were to find any vector that's kind of in the plane of the surface, it would make a 90-degree angle with it. Another could be kind of this side. So we define another vector, call it A2. Oops, not A squared. A2. A2 in this case looks like it has an area of 6 centimeters squared and seems to be pointing in the y direction. Again, it's perpendicular to that particular surface. Its magnitude is the area of that surface. And then there could be this slab here, which seems to be pointing, we'll call it A3. A3 looks like it has an area of 10 centimeters squared and points in the x direction. And then I could, all right, that's 3 of the 6 surfaces. I could define the other areas, or A4, A5, A6, which would look very similar to A1, A2, and A3, but with negative signs. As for each surface of the object, this area vector kind of gives us the orientation of the surface. This A1 tells me, since it points in the z direction, that this particular surface is in the kind of xy plane. Since this points in the y direction, this is in the xz plane. X direction, this is in the yz plane. Now in these cases, you know, the drawings I've made, there's kind of been a volume, right, that enclosed, right? There's this volume here, and all the arrows kind of point out of the volume. Here there's kind of a volume, and the arrow points out of the volume. That's a convention. But I did not need a volume to define this, right? I could have just had a slab, you know, a piece of paper that has some area. But then the question is, do I call this the area vector, which is perpendicular to it? or would I call this the area vector? And for just a kind of disjoint area slab on its own, it's up to you. All right, it's each one is fine as long as you specify and kind of are consistent. But the convention, which we will follow, is that if the surfaces encloses a volume, like the pillbox in the upper left or the rectangular kind of volume on the right. So if the surface encloses a volume, the convention is that the area vector points out. So it doesn't point into the volume, but points outward, from the volume. So we'll follow that convention. I think your book states that that's a convention as well, but if not, that's what we're doing. So then if we go back to kind of our bucket, if we have our bucket where this opening, the rain has to enter through this opening up top, so that is the surface that we wish to then define our area vector. If you want to think of it as the sensor, like I had it for the pipe, right? This is the sensor that has to flow past in order for it to be counted or counted for, right? And saying that yes, you've entered the bucket. But then if the velocity is flowing in some direction, now we have a way of talking about, if I go back a page, here at the bottom, right, how we talked about, here it seems like the velocity, the direction of the velocity mattered, but really it's the direction of the velocity mattered relative to the opening. Here the direction of really what I was doing here is I was saying something about what is the direction of the velocity relative to the opening in this case. So it seems like, and this is where I think a leap of insight will happen. If I have some area vector here and some then velocity vector here, then there's some angle that's defined between them. And again, if that's the area vector, then you can think of that this is where the sensor is. That rain has to flow past this particular location in order for it to go into the bucket. So what's going to determine? So that might be kind of a sketch of the surface. And again, for rain to enter the bucket, it has to flow past that surface. Well, we know enough about vectors that we can say whether or not it's going to flow past the surface. If you had a drop of water literally just hovering right above the surface, the only way that drop of water flows past the surface is if it has some component that will take it past the surface, which is this vertical component. If it only had this horizontal component, then even though it's really close to the surface, it would just sail on by and not go through. So notice that this is kind of the velocity that's perpendicular to A. This is the component of the velocity that is parallel to A. So it enters the bucket, whether or not the water enters the bucket requires that V have a component parallel to A. Or it can be anti-parallel or parallel anti-parallel. to A. And again, that's this component here. If it did not have this component, it only had this perpendicular component, then it would just kind of sail on by. Skim the surface but not go through it. Because it has this component, it will go, it might still be going to the right, but it will go nonetheless down as well and through the bucket, or into the bucket in this case. So it seems like it requires, right, so you need kind of V parallel, which is a component parallel or anti-parallel to A. That smells like a dot product. So it seems like we need something about the dot product. Because recall, the way we define the dot product is that if some velocity vector, and I dot it with, say, the unit vector A, points in the same direction of A, but has unit length, that could be defined, and that is indeed exactly V parallel, the component parallel or anti-parallel to A. Yeah, I could write parallel right to A to make it very clear. Right, that is, in a way, how you might define the dot product. So then the mass flux, this dm dt, which is a scalar, mind you. So whatever we do at the end of the day, we now have these two vectors flying around. We better get a scalar at the end of the day. Seems like the way we upgrade things is I only want the component of the velocity parallel to A. So I'm going to do instead rho, and then the velocity v dotted with the vector A. Note that still gives me the right units, right? So density times the velocity times an area. That will have units of mass per time. But because it's the dot product, this pulls out only the velocity component that is parallel to A. So in a sense, this is the same thing as rho v parallel, but then times A as well. It's not A hat, it's the original vector A, which has a magnitude of A. Or, given the definition of the dot product, that's the same thing as rho v, the magnitude, A, the magnitude, times the cosine of the angle between the two. And that, indeed, is a complete generalization of mass flux. It takes into account orientation as well. And given that it's a dot product, remember that a dot product returns a scalar, right? So this gives back a scalar. So all is well and good. And this, I think, even deserves a highlight. The mass flux. And again, there's something about kind of the fluid itself, rho times v, and then A is kind of giving us orientation of the surface that it's flowing through. So this rho times v ends up being what you can define to call a streamline. The streamline's a fluid flow. And it's completely analogous to field lines for electric field. In that I could write, instead of individual water droplets, I can talk about the path that water droplets would take. All the water droplets along this path are going to follow the same path kind of into the bucket. Same for these, same for these. And then if I have some sort of bird's eye view of a pipe that kind of expands out, then the streamlines here kind of expand out in this case, which might mean they slow down, or the density decreases or something. So for water, it's very hard to decrease the density. Increase the density rather. So probably this is saying something about how fast the water flows. Don't worry about that. But we can think of these like we do think electric field lines. But again, I think this is kind of easier to envision because something is literally flowing. I can think of water flowing along these lines where nothing really flows with electric field lines. So again, the mass flux in this case. The mass flux depends on properties of the fluid, the density, is it water or is it honey that's flowing by, as well as the velocity that's flowing, but also the geometry, because it's the vector v, the direction of these streamlines. And then it's dotted with a, this vector that quantifies the surface that it's trying to flow through. And again, you could think of that, when is the dot product 0? Well, the dot product is 0 when the two vectors are perpendicular to one another. So does it make sense that this should be 0, the mass flux should be 0 when they're perpendicular to one another? Well, I could draw the velocity v, going like that. Then if I wanted the area to be perpendicular to that, I could draw maybe the area like that. But then again, what we have to remember is that, back up here in the definition of how we defined A, that means the surface itself, the sensor, looks something like this. In which case, indeed, the water is not going to flow through the surface, but it's going to kind of just skim over it. Or if it's right beneath it, it will just skim right beneath it. It will not actually flow through the sensor. Versus if they're, say, parallel to one another, and say if A is like this, well, then that means the sensor, or the surface, looks like that. And indeed, that's going to be probably the best way to have things flow through. Because I know if it's at an angle, less streamlines will flow through. So, the dot product does seem to make sense in this case. It's giving us the right values in terms of whether it's non-zero or 0. Jumping over and going to the bottom here, again, we can also think about the sign from whatever class we worked that out as one of the problems. Right, this dot product is greater than 0. And we worked it out that the dot product is positive when these two are closer to being parallel to one another. So like this, they're exactly parallel to one another. There, the dot product is going to be positive. Or if V was kind of at an angle, but it's less than 90 degrees, the dot product is still positive. So what this is also saying is that the mass flux is going to be positive when V and A are less than 90 degrees from one another. So when they're closer to being parallel, the mass flux is positive. This is a positive mass flux. The mass flux is 0 when they're perpendicular. And to flesh out the other example, right, I'll just do the extreme. Right, if the velocity and the area are completely anti-parallel, the dot product is negative. In that case, then the mass flux is defined to be negative. So in this case, you kind of see that it's positive when V is flowing in kind of the same direction as A. If V is going in the opposite direction as A, then that's negative. This is just a convention, right? You can always add a negative sign, to get for whatever you're doing, if necessary, which we'll do in the next problem. So this is not a perfect analogy, but it might help your understanding to think of this as kind of a way of counting streamlines. Because this is essentially telling you how many streamlines there are and kind of what concentration there are of streamlines. So you can think of this as kind of being a way of as kind of quantifying the number of streamlines. And then these streamlines are moving through a surface. So this mass flux, you can think of, again, roughly, it's not perfect, as kind of counting the streamlines that are moving through a surface. And why this is not perfect, of course, is because the dot product extracts a component. And so when you can't extract a component when you're counting, right? Either 0, 1, 2, 3, with counting. But really, this is extracting a component. But as long as you remember that it's not a perfect analogy, I think it still works pretty well. If in terms of counting field lines, right? If there are many field lines going through a surface, that's going to be a larger mass flux than if there are only like a few going through the same surface. So you can think of this as counting field lines. Let's now solve the original problem. So rainfall, let's say rainfall falls at about 1 meter per second at an angle 3 degrees from vertical. How fast does an open lid soda can, so imagine a soda can, but you cut the top so the entire top is open, which has a height of about 123 millimeters and a diameter of 66 millimeters. How fast does that fill up? Well, we have to consider that rain is falling at an angle, so I've drawn it here, kind of 3 degrees from vertical. And it has to flow through this surface. This is the surface that constitutes whether it goes into the bucket. So that's going to define my area vector for that particular surface. It has to flow through that surface in order to count. Now there is a vertical component, or component parallel to A, in this case anti-parallel to A. So the water droplets can flow through the surface. But we need to incorporate kind of our dot product formula. So if that's 3, then this is 177 degrees, which is what I would call theta. The area here, so it seems like we have the magnitude of this area vector, which is then going to just be pi r squared, or pi times kind of 0.033 meters. We'll switch to MKS units, of course. Right, so that ends up being 0.0034 meters squared. And just for when we plug in some numbers. Cosine of 177 degrees is, of course, by trig identities, the same thing as negative cosine of 3 degrees, which you punch that into your calculator, is negative 0.999. It's pretty close to being 0. 3 degrees is pretty close to being 0 degrees. So I expect it to be pretty close to 1. Indeed it is. And again, note the negative sign, because A and V are much closer to being anti-parallel than they are to being parallel. And then we have a value for the velocity is 1 meter per second. And we also have a value for the density of rain, which we'll take from before as 1 gram per meter cubed, but that's not MKS, so we'll 10 to the negative 3 kilograms per meter cubed. Okay, and then we want to calculate dm by dt, the rate that the bucket is filling up. But then notice, because of that, of our convention, right? The convention that A points outward, since this is kind of a closed volume, so we wrote A pointing this way instead of A pointing that way. Note, because of this convention, it seems like we're going to get a negative dm by dt. Essentially, this negative here is going to propagate. So I'm just going to throw a negative sign in here. So this is going to be negative rho rain, then velocity dotted with A. And again, just because I want to think of dm by dt as being positive when it flows into the bucket, but because A and V are anti-parallel by the convention, right, I'm just doing it to get the sign right. So in this case, again, what's the dot product? It's negative rho times rain, the velocity, the magnitude of the velocity, the magnitude of A, times the cosine of theta. I have all those numbers, I can plug them in, and I get 3.24 times 10 to the minus 6 kilograms per second. All right, that is how much mass per second enters my can. Now, of course, I want to figure out how fast the bucket's filling up. And if you haven't done related rates yet in calculus, this part, consider optional. All right, this as an aside. All right, that the rate that the water's height can also be calculated. Because you can imagine as water flows into this bucket, right, it's going to collect at the bottom of the bucket, and then it's going to eventually fill up slowly but surely. And so if I draw the bucket after some water has filled it up, right, I can imagine kind of there's water that's filled it up, partially. And maybe it's at a height h so far. And I could think, okay, what is the volume of the bucket where water is filled up, right? The volume that has been filled up is going to be pi r squared. That's the area multiplied by h. Right? That volume is filled with water based on the drawing. And so the mass in the bucket is going to be, well, that's a density times a volume. Here is going to be the density of water, not rain, but the density of water times pi r squared h. Why is it the density of water? Well, of course, the density, right, it's actually water here. It's not rain with a lot of air, water droplets with a lot of air in between. But here it's collected and it's actually become just liquid water rather than kind of, rain or water vapor, depending on how heavy or light the rain is. So the related rates problem is that I could then ask, okay, what is dm by dt? Now, there are three variables here, rho water, r, and h, but only one of them is changing, right? Rho water is a constant, the radius of a tin can is a constant, but then h is the thing that's slowly but surely getting larger. So I treat everything else like a constant, right? So then rho, pi, r squared, those are all constants, and multiplied by the derivative of h, so I get dh dt. So I can connect dm dt to dh dt. But then I have my previous result. I also wrote that negative rho rain, velocity times area, which is dm dt, is now going to be equal to rho water pi r squared times dh dt. And the thing on the left side, the area, again, I'll work in symbols first. Rho rain, negative rho rain. Then I have v, and then the area was pi r squared. And there's the cosine of that 177 degrees equals rho water pi r squared dh by dt. And again, nice when you don't plug in numbers too quickly, because then it's like, oh look, the pi r squareds, those cancel. And then I can very easily solve for dh by dt. Looks like it is negative rho rain divided by rho water times v times cosine of theta, which this ratio, we said at the very beginning, was about a millionth. So it looks like it's negative 10 to the minus 6 times 1 meter per second times cosine of 177 degrees. Note the velocity is the only thing with a unit, which is a length over time, which is great because that's what dh by dt is. It's a length divided by a time. This, at the end of the day, you plug in numbers, you get 9.99 times 10 to the minus 7 meters per second. And it turns out when you do the conversion, that becomes something like 3.6 millimeters per hour. Which if you look up kind of rainfall, or what's a large amount of rainfall versus a light amount of rainfall, they will usually give a number that's something like millimeters per hour. They might give like inches per hour as well, but you will typically, in the metric system, you will typically see it's like the rainfall was, like moderate rain is kind of in the kind of three-ish millimeters per hour. A very light rain might be 1 millimeter per hour. very heavy rain is above 10 millimeters per hour. So in this case, and again, this is saying that if you had a bucket, the height of the water would fill up at a rate of the height of the water in the bucket would fill up at a rate of 3.6 millimeters for every hour. So as a kid, right, if you measured kind of, if it was raining for 2 hours and you had measured, the bucket went from 0 to some height, right, then that height divided by 2 hours would give you some measure of kind of the rate, which is how this is usually quantified. That's more of an aside. Another aside I would point out is, do check your work. Here's one example of how AI does not get it right for quite a absurdly simple unit conversion problem. I just didn't want to do it. It was late. So I just asked it, here's the number, please convert it for me. As you can see, this is the completely wrong answer. Wrong. And then it fixes itself and actually gave me the right answer. What it learned here versus here, I do not know. But again, check your work. Don't just take what this thing tells you, as an absolute given. All right, we're almost done. A couple of little elaborations. In the case of these surfaces here, let me go back to these examples. In the case of all these surfaces were flat, where it was very easy to define kind of what the area was. It's all flat and kind of one plane. Right, this was entirely in the YZ plane, so I knew how to I drew this in the X direction. This is entirely in the XZ plane, so I knew to draw it in the Y direction. What if it was something that was more curved? Like, what about the side of this pillbox, right, where there's essentially 3 surfaces on this thing. There's the top, which in this case was the opening. There's the bottom, the base. But then there's this side part, this kind of, you can imagine like a strip of paper, looped around in a circle, that forms the side of the cylinder. What direction do I draw A? Because, this part, right, the A is kind of over here, and this part, the A is over here, in order to make it perpendicular, right? How can I draw these arrows to be perpendicular to the surface? Which one of those is correct? And there's the ones behind it as well. And again, because I think the water helps us kind of understand this better. Let's suppose your friend wants to join in on the fun, but not really understanding the exercise. Their bucket that they put outside is a colander, right? So it's kind of a semicircle thing that has a bunch of holes in it. Usually used to drain pasta or vegetables or whatever. So in that case, rain comes in, and we could quantify, okay, that makes sense. There's this surface here, this flat surface, which I'll call that the area of that surface. But then the water, once it gets in, starts to kind of come out in different directions as it goes through the holes. What is the surface in that case? Or, to give another example, what if I had a very well-defined flat surface? Should have used red. Right, so that's my area vector I might use. But the rain is flowing or falling non-uniformly. So maybe on this side it's kind of very light, but then it's rain is falling. More droplets are kind of falling on the right side. Maybe it's a large tarp where there is a difference from one side to the other. In this case, in both these cases, as you might imagine, we just take the calculus limit. So in this case, I can imagine, since I can't really define one vector for the side of the colander, I could just break it up into a bunch of small pieces, right? Each with little dA. Over here, then this one goes that way, and this one goes that way, such that each dA points makes a 90-degree angle, points perpendicular to the surface in that region, right? This vector here is perpendicular to the surface, really only right there. But I'm breaking up the surface into a bunch of smaller little pieces. Similarly, for the sheet or the tarp, you can imagine I could break the thing up into a bunch of small little pieces of area. And each of those get their own little vector dA. And this one gets a dA, and this one gets a dA. Everyone gets a dA. But then I could think about, if I want to calculate the flux, let's stick with the tarp. What I should do with the tarp is essentially then I have to add up, right? Then you just kind of add up, the flux through kind of each small dA, right? I've broken the area into a bunch of little bits. Similarly, for the colander, again, I have taken the side of the colander and broken it up into a bunch of tiny little bits. Well, I know that the area is going to be just the integral of all these little bits. So the generalization is that I could write that the flux, the mass flux in this case, there's going to be rho, there's going to be v, but then that v might be different, in different regions of the tarp, or the area itself might be a curved surface. So if I break them up to a bunch of dAs, but then I just have to add them all up. So this is kind of the most general, formula. Which, when you have a nice flat surface, right, you don't have to do the integral. It's just rho v times the kind of area vector A, like what we did in all the examples so far. But if you have one of these kind of curved surfaces, like the colander, or if v itself is a more complicated function, like it is over here on the tarp, then you can just break it up into a bunch of smaller pieces that you then add up. So this is the general formula. And then we're essentially done. Essentially then I can define the electric flux exactly the same way. Instead of rho v, I'm just going to replace it with the electric field E. So then this defines the electric flux through a surface. Give me some surface, and then if I have an electric field, so here I have a positive charge, there's electric field lines. Some of them are going through the surface, right? These three here are going through the surface. I could calculate the flux through that surface. Again, you can think of it as counting field lines, but that's not perfect because each of these field lines is hitting the surface at a different angle. This one is kind of almost perpendicular, but these are kind of at a slight skew relative to the area, relative to this surface rather. So I could then ask about the electric flux. And here's where I think it's useful, right, to again have that water analogy, because again nothing's flowing with electric field lines, but you can still talk about the flux of the field. But if you want to think of it as kind of flow, right? I kind of sometimes in my mind I imagine like the charge is kind of pulsing, like it's glowing, right? And I think of like pulses of light kind of like moving down the field lines, right? If I want to imagine something as if it's flowing, so you would have like a boop, 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 kind of moving through. If that's helpful, that might be nonsense. Whatever. So, and what we'll do in class is we can now think of, just like what we did in the previous questions, we could think about how we might calculate electric flux through a particular surface. So let me do a few of these, and then I think I might leave some of these for what we do together in class. Let me just do the first one, and then I'll just write down the answers for the others. So I have some positive charge, and I want to ask myself, what is the flux through this spherical surface? So I've drawn a big sphere around the charge. It has radius capital R. And I want to ask myself about the electric flux. So I can imagine drawing field lines, And they're all going to go out from the charge. So they're all going to eventually pierce through the surface. You can imagine them kind of piercing through as it goes outside. And then since this is a curved surface, right, I can't write down a single area vector. I really have to write down a bunch of little dAs. Right? Each little part of the sphere has its own little dA that points perpendicular away from the sphere. Well, the nice thing about this particular surface is that the dAs always are going to be parallel to E, right? Because they're both always going to be pointing kind of radially away from the charge. If I drew a cube around this thing and asked what's the flux through the cube, that would be a much harder problem because the electric field lines do not hit all at the same angle through the surface of a cube. It would be kind of a very messy integral to do. But here, the fact that E and dA are all going to be always parallel to one another is actually going to serve us a lot. So then if I want to calculate the flux, which is going to be the integral of E dot dA, right? I'm going to calculate what it's doing at every little piece and then add them all up. Well, that's equal to the integral of the magnitude of E, the magnitude of A, which I'll just write as dA, multiplied by the cosine of the angle between them. But we just said that they're all parallel. So cosine of 0 is 1. Looks like this flux is going to be the integral of E multiplied by dA. Now the next thing to think about is the sphere is the same distance away, right? Every one of these dA elements, right? Because this is the magnitude of the electric field at each of these dAs, right? Because I could think of it as, right, the magnitude of the E field at this point times this dA. Then I add to that the magnitude of the E field when it's here times this dA, and the magnitude of the E field here times this dA, and here and here and here and here. And I have all these little pairs of E and dA all over the sphere. But we know that the electric field goes as 1 over r squared. It's radial. So we know that the electric field is actually the magnitude of the electric field is the same at all the points on the sphere, because they're all the same distance away from the charge. So this magnitude of the electric field is a constant, right? So we can pull that out, and then it just looks like the integral of dA, which I add up all the little bits of area to make a sphere. I know what that is. That's E, then 4 pi capital R squared. So it seems like we've said that the flux is a positive number. The flux is equal to 4 pi r squared times the magnitude of E. But we know the magnitude of E. If you're a distance r from the charge, we know that this is going to be, it's a positive charge, so I won't bother with absolute value. We know that that is Q 4 pi epsilon naught r squared, right? That's the magnitude of the electric field a distance r away. So notice that 4 pi and the r squareds cancel. And it looks like at the end of the day, I get positive Q over epsilon naught. Interesting. Maybe not. But the next 2 days you will say, yes, interesting. In this case also, note that there's more field lines, right? Let me just set the stage. There's more field lines leaving than entering. More field lines are going out of the surface than entering. Contrast it with this one, where I have essentially the same exact problem, but I have a negative charge in the middle. And I'll use a different radius as well. Here, the electric field is always going to be pointing anti-parallel, so it's going to be pointing inward. But then everything else is the same in terms of our argument. So it turns out the flux in this case ends up being negative the magnitude of E times 4 pi little r squared. But then that becomes negative absolute value of Q, this is the magnitude of the electric field vector, 4 pi epsilon naught little r squared, that's just the electric field, times 4 pi little r squared. This turns out to be negative absolute value of Q over epsilon naught. Or I'll just write as Q over epsilon naught, because Q itself is negative in this case. It's negative E. So it's less than 0. So it looks very similar, but it is a negative number instead. In this case, more field lines, more field enter than leave. In this case, they're all entering, right? They're all going into the surface, and the flux is negative. And there's also a negative charge in there. Where for the first one, they're all leaving the surface, and the flux was positive. There's also a positive charge in there. And last but not least, imagine you have a positive charge, but then my surface is kind of this shell, this thick shell, where it has an inner radius of little r and an outer radius of bigger R. And there's kind of a hole in the middle, where there's also a charge. So then the flux, the field lines kind of shoot into the surface and then shoot out of the surface. In this case, they all enter on the inner cavity and leave the outer cavity. But the flux lines are going to be always either parallel or anti-parallel to A. And it turns out that when you measure the total flux going into the shell, right, all the field lines that go into the shell also leave the shell. Right? Once you go in, you go out. So it turns out the flux ends up being 0. Essentially, the net flux ends up being 0. What goes in comes out. And if I think about what is inside the shell, not inside the cavity, but inside the shell, there is no charge inside the shell. And yet, so when there was no charge inside the shell, all the flux that went in also went out. When there was a charge inside the shell, and more field lines went in, it was negative. When there was a charge inside the shell, and more field lines went out, it was positive. We'll do some other problems in class that I think will help motivate that there's something going on with all of this. There seems to be a connection between perhaps the flux. There's some connection between the flux and kind of the presence of charge, where if the charges which are acting kind of as sinks, right, field lines go and get kind of sucked in, or sources where they're kind of the origins of field lines, you have a net flux. But when I'm just considering something that does not have a sink or a source, the flux seems to be 0. This is essentially what Gauss's law is trying to say, which we'll do next time.